Hello and welcome. My name is Michael Rosenbrock. I'm a content specialist for leadership and STEM at Evidence for Learning. My background is working in schools in the state system in Victoria, most recently as assistant principal at Wodonga Senior Secondary College. Prior to career changing into teaching, I was an aerospace engineer working in the aerospace and automotive industries in Germany, the United States and Australia. Today, I'm going to give you a brief introduction to Evidence for Learning's newly released guidance report, Improving Secondary Science. I'd like to start by acknowledging the traditional custodians of the land on which we meet and pay my respects to elders past and present. I am on Pangarang land in northeast Victoria today, so I particularly acknowledge their elders past and present. At E4L, we also accept the invitation in the Uluru Statement from the Heart to walk together with Aboriginal and Torres Strait Islander peoples in a movement of the Australian people for a better future. Evidence for Learning is an independent not-for-profit that works across all states, territories and sectors. Our mission is to help busy educators increase learning for children and young people by improving the quality, availability and use of evidence in education in Australia. We were founded in 2015 and operate as part of Social Ventures Australia. We partner with international evidence brokers, including our founding partners in the United Kingdom from the Education Endowment Foundation. Today, I'm going to provide some insights into our newly released guidance report, Improving Secondary Science. This guidance report makes 7 recommendations to assist school leaders and science teachers to use their precious resources well by focusing on the best bets that are most likely to have a positive impact on student outcomes. You can find the full guidance report and supporting resources on our website at e4l.org.au/sciencesecondary. So without further ado, I will now briefly unpack each of the recommendations and provide a preview of the supporting tools. The first recommendation is focused on preconceptions and building on the ideas that students bring to lessons. Students' own explanations for phenomena may differ from scientific ones. Cognitive conflict and discussion are effective ways for moving on students' thinking. Misconceptions can be difficult to shift, but doing so can lead to big learning gains. It is usually necessary for students to go through a process of adjusting their ideas as they develop a more scientifically accurate understanding. The example here from the guidance report looks at cognitive conflict. In this case, the common misconception is that something must fill the gaps between particles in a gas. Via a brief activity to show that a syringe cannot compress a liquid, in this case water, but it can compress a gas, such as the air in the classroom, students are provided with a situation that cannot be explained without a vacuum between the particles. One of our supporting resources is the RADAAR planning tool, which is designed to assist in planning to address misconceptions. The prompt questions step through the process of planning a lesson or learning sequence that addresses misconceptions. Researching and anticipating misconceptions, including the role of language and links to previous topics. Diagnosing misconceptions and addressing them in class. And assessing and reviewing, including considerations of links to future topics. There are also prompts for reflection, considering does anything need reteaching, does vocabulary need to be revisited, and have any concepts not stuck. Whether used individually or across a department, this is a really useful tool for explicitly addressing misconceptions in science. The second recommendation in the guidance report is around self-regulation and helping students to direct their own learning. These skills need to be developed within the context of learning a subject, such as science. Studies show strong links between self-regulation and achievement in science. Strategies include explicitly teaching students how to plan, monitor and evaluate their learning, modelling thinking, and engaging students in metacognitive talk. The example here from the report illustrates the metacognitive regulation cycle as an ongoing process of planning, monitoring and evaluating as a student progresses through a task. The third recommendation is focused on modelling and using models to support understanding. Models should be selected with care and the ideas they are based on should be familiar to students. Students need to be explicitly taught about models and be encouraged to critique them. It is important that students understand how models differ from the idea being taught and learn the underlying idea rather than learning the model. An example here from the report is the barrel analogy for the effect of limiting nutrients on plant growth. The wooden stave from the barrel that represents the nutrient potassium is the lowest, so it is where the water is leaking out, representing the situation where the growth rate of a plant is limited by potassium. Another example of our supporting resources is the FAME approach for worked examples. This helps to unpack key considerations for effectively using worked examples via 4 components. Fading is the process of gradually removing or reducing elements of full worked examples, moving towards independent practice. Alternation highlights the value of alternating examples with opportunities for student practice before adding variation or additional complexity. Mistakes focuses on how to effectively use mistakes in examples to provide further challenge, whilst being careful not to do so too early, as this could embed misconceptions. Explanation highlights the importance of teachers modelling their thinking aloud and supporting students to do so when working with their peers as well. The 4th recommendation is focused on memory and the importance of supporting students to retain and retrieve knowledge. Cognitive science has led to breakthroughs in our understanding of brain functions and processes. Research supports paying attention to cognitive load, revisiting knowledge via spaced review, the use of retrieval practice, and the value of elaborative interrogation. An example from the report here of how we can reduce cognitive load is by avoiding split attention. In these 2 diagrams of the heart here, diagram A on the left has the labels integrated with the visual, meaning that students can focus on making meaning out of the diagram. Diagram B on the right has a key, so students must move their attention between the visual and the key, doing quite a lot of processing, and splitting their attention from making meaning of the actual content on the diagram. The 5th recommendation is focused on practical work and using it purposely as part of a learning sequence. It is important to be clear about your purpose for choosing a particular activity and that practical activities are undertaken in a considered sequence with other learning. Practical work has positive impacts on the development of specific practical skills, as well as developing scientific reasoning skills. We have an example here from the report adapted from Miller and Abrams, which provides a useful framework for assessing the effectiveness of a new practical activity. This looks at where students are hands-on and minds-on, and unpacks where the students both did what was intended and whether they learnt what was intended. A really useful prompt for planning and reflecting on practical work. The 6th recommendation is focused on the language of science and developing scientific vocabulary and supporting students to read and write about science. Students need to be explicitly taught scientific vocabulary. It is not possible to explicitly teach every potential word, so it is more important to carefully select what to teach and prioritise the most challenging words. Showing the links between words is efficient and it aids understanding. The example here from the report looks at the morphemes that make up the word photosynthesis. Explicitly teaching this to students can both help them to build an understanding of and remember the particular word, as well as giving them further knowledge that they can use to understand words that use the same or related morphemes. Extended reading and science writing can help develop understanding. The report includes further suggestions for ways to support students to engage with text and develop writing skills. The 7th and final recommendation is focused on using structured feedback to move on students' thinking. The type of feedback matters. A range of strategies should be used to uncover students' understanding. Feedback should help students develop as learners, and it is most effective when students know how to respond and are given time to do so. Looking at this table from the report adapted from Fletcher Wood, which unpacks the different types of feedback, provides a good example of where feedback may not be effective. Feedback on self-regulation is valuable as it is focused on aspects that can be acted upon to bring about improvement. This contrasts with feedback focused on self-evaluation, which is really more about good or bad, suggesting that abilities are fixed and does not provide any direction, steps, or even necessarily motivation for improvement. Another of our supporting resources is the Using Research in Science Teaching poster. This poster unpacks each of the recommendations, what the research is telling us, along with examples of each recommendation. And then it provides a number of application examples that bring together 2 or more recommendations in an activity that you might use in class. A really valuable resource for exploring examples of practice and considering how you might use the guidance report to shape your own practice, or as a stimulus for discussion and reflection as a team, department, or even as a whole school. The final supporting resource I'd like to share with you today is our self-assessment tool, or Red, Amber, Green. This guide has a section for each of the recommendations, providing a detailed continuum that can be used to reflect on current practice, either personally or as a team, and identify areas of focus for improvement. I'd like to thank you for watching this briefing on Evidence for Learning's new guidance report on improving secondary science. You can access the guidance report and supporting tools via our website at e4l.org.au/sciencesecondary. If there is something that you have found particularly useful from this resource, would like to share how you've put those resources or recommendations into practice, or you have any questions, you can get in touch with us via email. To stay connected, sign up to our newsletter and follow us on social media. Thank you very much.